Welcome to our exploration of biocompatibility, a crucial concept in the field of artificial organs and medical implants. In this video, we'll break down what it means for a material to be biocompatible and why it matters for anyone working with or receiving medical devices. We'll also dive into the fascinating world of the immune system, which plays a central role in determining whether a material is accepted or rejected by the body. Let's start by understanding the basics and setting the stage for a deeper dive into the science behind biocompatibility. The term biocompatible refers to how suitable a material is for use inside the human body. This suitability is determined by how the body reacts to the material, especially through its immune response. If a material triggers a strong negative reaction, it's not considered biocompatible. On the other hand, if the body accepts the material with minimal adverse effects, it's deemed suitable for medical use. Understanding this concept is vital for developing safe and effective artificial organs and implants. Immune system is the body's defense mechanism, protecting us from invading microbes and maintaining internal balance. It's made up of three main components: physical barriers, immune cells, and circulating proteins. Each of these plays a unique role in keeping us healthy and responding to foreign materials, such as medical implants. Let's take a closer look at how these components work together to determine biocompatibility. Physical barriers like the skin and surface tissues act as the body's first line of defense. They form protective walls that keep harmful microbes out. When these barriers are breached, such as through cuts or burns, the risk of infection increases dramatically. This highlights the importance of maintaining healthy barrier tissues, especially when considering surgical procedures or the implantation of artificial organs. Over the past 2 decades, medical advances have dramatically improved survival rates for burn victims. Previously, burns covering half the body were often fatal. Today, with better resuscitation, wound care, nutrition, and infection control, patients with burns covering up to 90% of their bodies can survive. Grafting with natural or artificial materials also speeds up healing, showcasing the importance of biocompatible materials in modern medicine. When a surgical implant is placed in the body, it breaches all of the body's natural epithelial defenses. This means the immune system is immediately alerted to the presence of a foreign object. The body's response to this breach is a key factor in determining whether the implant will be accepted or rejected. Understanding this interaction is essential for designing safer and more effective medical devices. The primary job of the immune system is to eliminate infectious agents and minimize the damage they cause. Every immune response starts with recognizing a pathogen or foreign material, followed by a reaction to eliminate it. This process is at the heart of how the body interacts with implanted materials, making it a critical consideration for biocompatibility. There are two main types of immune responses: innate and adaptive. The innate immune system acts quickly and is the body's first responder, but it doesn't adapt to repeated exposures. The adaptive immune system, on the other hand, is slower but highly specific, learning from each encounter and providing long-term protection. Both systems work together to protect the body and influence how it reacts to implants. The innate immune system is the body's rapid response team. It reacts quickly to any invader regardless of its identity. This system is nonspecific, meaning it doesn't distinguish between different types of pathogens. Instead, it provides a broad defense, buying time for the more specialized adaptive immune system to kick in. The innate system is crucial for immediate protection, especially when barriers are breached. Adaptive immune system is slower to respond but highly specific. It learns from each encounter with a pathogen, building a memory that allows it to respond more effectively to future threats. This system is responsible for the body's long-term immunity and plays a key role in determining whether an implanted material will be tolerated or rejected over time. Innate and adaptive immune systems don't work in isolation. When the innate system detects a threat, it signals the adaptive system to activate. This dynamic interaction ensures a coordinated and effective defense against invaders, including foreign materials introduced by medical implants. Understanding these dynamics is essential for predicting and managing the body's response to biocompatible materials. Immune system is a complex network of specialized cells that communicate through cell surface signals and soluble proteins. These interactions influence how immune cells behave and coordinate their responses. This intricate communication system is at the core of how the body recognizes and reacts to foreign materials, making it a key factor in biocompatibility. T cells are a type of lymphocyte that play a central role in the immune response. Cytotoxic T cells target and destroy virus-infected cells, foreign tissues, and tumor cells by recognizing specific antigens and releasing toxic chemicals. Helper T cells, on the other hand, activate other immune cells like B cells and natural killer cells, amplifying the body's ability to fight off infections and abnormal cells. T cells are another type of lymphocyte produced in the bone marrow. Their main job is to make antibodies, which are proteins that specifically target and neutralize foreign invaders. When activated, B cells can differentiate into plasma cells that secrete large amounts of antibodies, or become memory cells that provide long-term immunity. This process is vital for both fighting infections and determining how the body reacts to implanted material. Phagocytes are immune cells capable of engulfing and digesting foreign particles, microbes, or even damaged cells. The main types in mammals are neutrophils and macrophages. For biomaterials, the behavior of phagocytes is especially significant, as they are often the first to interact with implanted materials, influencing the overall immune response and biocompatibility. When a foreign material enters the body, phagocytes from the innate immune system are the first to respond. They consume the intruding microbe and display its antigens on their surfaces. These antigens are then presented to the adaptive immune system, which is stimulated to mount a more specific and powerful response. This sequence is crucial for understanding how the body reacts to implants and artificial organs. Antigen presentation is a key step in the immune response. After phagocytes digest a microbe, they display its antigens on their surfaces. These antigens are recognized by cells of the adaptive immune system, triggering a targeted response. This process ensures that the body can specifically identify and remember foreign invaders, which is also relevant for how it reacts to implanted materials. B cells encounter an antigen. Sometimes with help from helper T cells, they become activated. Activated B cells proliferate, creating many copies of themselves. Some of these become plasma cells that secrete antibodies specific to the antigen, while others become long-lived memory cells. This process is essential for both immediate defense and long-term immunity, influencing how the body responds to repeated exposures. Clonal proliferation refers to the rapid multiplication of activated B cells. Some of these cells become plasma cells, which are short-lived but produce large amounts of antibodies. Others become memory cells, which persist in the body and provide long-term immunity. This dual response ensures that the body can fight off immediate threats and remember them for the future. Antibodies are specialized proteins produced by plasma cells. They bind specifically to antigens, neutralizing foreign invaders and marking them for destruction by other immune cells. The production of antibodies is a cornerstone of the adaptive immune response and is critical for both fighting infections and determining the body's reaction to implanted materials. In summary, biocompatibility is all about how the body's immune system interacts with foreign materials. From the first line of defense provided by physical barriers to the complex interplay between innate and adaptive immunity, every step plays a role in determining whether an implant will be accepted or rejected. Advances in our understanding of these processes continue to improve the safety and effectiveness of artificial organs and medical devices, offering hope for better patient outcomes in the future.